Solar eclipses. Humanity has been fascinated with them since the ancient times. They are the result of the moon getting in the way of the sun, and you may even know the splendid word used to describe the collinearity of celestial bodies that allows for their occurrence. Solar eclipses come in three types: total eclipse, where the moon completely blocks the sun; partial eclipse, where part of the moon blocks part of the sun; and annular eclipse, where all of the moon is blocking the sun, but the sun still shows in a ring around the moon. But wait, if the moon orbits the Earth every month or so, why doesn't the Earth get a solar eclipse every month? And why are the paths that solar eclipses take so interesting, and not always along the equator? And how could the moon sometimes be large enough to completely block the sun and cause a total eclipse, while at other times be small enough to cause an annular eclipse? Welcome to TwoLambdaPlusBlack. I am Heirua. Imagine a single light source shining on a spherical object. If the light source is a point, one could draw a cone emanating from the point and tangent to the sphere. Points beyond the sphere inside the cone will be in the sphere's shadow. With just this one light source, an observer outside this cone will be in light, and an observer inside this cone but beyond the sphere will be in complete darkness. If the light source is not just a point, though, the shadow situation gets a bit more interesting. Suppose the light source is also a sphere, but smaller than the spherical object causing the shadow. An observer in most areas will still be in the light, and an observer behind the object will be in total darkness, like in the point light source scenario. But there is now a region between these two where the object blocks some, but not all, of the sphere of light. This too is a shadow of the object, but it is a different type of shadow. A shadow where there is less light than out in the open, but it is nowhere near total darkness. We call the shadow of total darkness the Umbra, and the shadow of partial darkness the Penumbra. If the light source is a sphere that's larger than the spherical object in the way, the situation becomes more interesting still. First of all, the Umbra is now finite. Think about it. If the sphere from which the light is coming is larger than the obstructing object, then if you keep backing up, eventually the object will no longer be able to completely block the light source in view. And even if you're centrally aligned with the obstructing object, light will eventually reach you from the source, starting as a ring around the obstructing object. And an observer in this situation is in a third type of shadow, the Antumbra. Like in the Penumbra, it is dimmer than out in the open, but it is not total darkness. Okay, now let's consider solar eclipses. The sun is the spherical light source, the moon is the much smaller obstructing object, and the location on Earth is where an observer of an eclipse is. If an observer is in the umbra of the moon completely obscures the sun, and the observer experiences a total eclipse. If an observer is in the penumbra of the moon partially obscures the sun, and the observer experiences a partial eclipse. And finally, if the observer is in the antumbra of the moon, all of the moon is obscuring the sun, but fails to obscure the entire sun, and the sun still shines in a ring around the moon, producing an annular eclipse. Umbra, total; penumbra, partial; antumbra, annular. Now, think about the fact that the Earth is much larger than its moon. Consequently, only a tiny fraction of its surface can be inside the umbra or antumbra of the moon at a given time. As such, during any solar eclipse, only a small path traced across a section of the Earth's surface gets to experience a total or annular eclipse, if at all. In the former case, this path is called the path of totality. Around this path, though, a much larger area of the Earth's surface will fall inside the penumbra, and observers in this much larger area will get to experience a partial eclipse. It's also possible that the umbra and antumbra miss the Earth completely, but the much wider penumbra does hit the Earth, in which case for that eclipse only a partial eclipse can be observed from Earth. Consider the situation where a planet's moon manages to block the star the planet orbits, tracing the same shadow across the equator of that planet on each orbit. Let's see what assumptions we've made that do not hold in the situation with the Earth and its moon. First, we've assumed that the orbit via which the moon revolves around the planet is on the same plane, or coplanar, with the orbit via which the planet revolves around the star. If you imagine that a planet's moon orbited the planet along a plane far inclined from the planet orbit plane, it shouldn't be hard to see that the moon could easily make an entire orbit without ever casting a shadow on the planet. If this shadow traces the planet's equator, we've made the additional assumption that the planet's equator is coplanar with the planet's orbit, or in other words, that the planet has no axial tilt. Thinking about the other question, if we reason that the moon should always stay the same size relative to the star, then we're assuming that the moon's orbit is a perfect circle. In thinking a bit further, we can realize we're also assuming that the planet's orbit around the star is a perfect circle. Eccentricity and inclination are two quantitative properties of orbits. Kepler's first law of planetary motion requires that an object orbiting another object in space necessarily has an elliptical orbit, but does not necessarily have a circular orbit. With any elliptical orbit, we can speak of its eccentricity, a quantity at least 0 and less than 1, essentially a measure of how elliptical the orbit is. An orbit with an eccentricity of 0 is a perfect circle, and the greater the eccentricity is, the more elongated the ellipse is. Earth's orbit around the Sun is nearly a perfect circle. Its eccentricity is 0.02. Inclination is the angle of tilt of an orbit from a reference plane. When we speak of the inclination of a moon's orbit, our reference plane could be either the plane of the planet's equator or the plane of the planet's orbit. Earth's moon is an example of a regular moon. The term regular moon is what we use to refer to a moon that orbits relatively near the planet and is likely formed with or from the planet, whereas an irregular moon orbits relatively far from a planet and is likely a captured asteroid. It turns out that among the solar system's regular moons, Earth's moon is very special. Most regular moons in the solar system have orbits with really low eccentricity and really low inclination. But for Earth's moon, both its eccentricity and its inclination, while still small, are non-trivial. Let's revisit the questions we asked earlier. Why isn't there an eclipse each time the moon orbits the Earth? And why can our moon produce both total and annular solar eclipses? The answer to the first, the moon's orbit is significantly unaligned with the plane of Earth's orbit, which we call the ecliptic, specifically by 5.1 degrees. It's worth noting that even though 5.1 degrees may not sound like much, Earth's radius is 6,300 kilometers, whereas the distance from Earth to the moon is 360,000 kilometers at perigee, that is, when the moon is closest to the Earth. And 360,000 kilometers times the sine of 5.1 degrees is substantially larger than 6,300 kilometers. So 5.1 degrees would be enough inclination to make solar eclipses fairly rare. Because the Earth has an axial tilt, though, there is a second reason for the path of solar eclipses to not be parallel to latitude lines. These paths could move north or move south, but they generally move from west to east, because even though the moon orbits the Earth in the same direction as the Earth rotates, the Earth takes just a day to rotate, whereas the moon takes 29 days to revolve around the Earth. By coincidence, the moon and sun have nearly the same apparent size in the sky from the perspective of the Earth. In fact, they are so close that despite the moon's orbit having an eccentricity of only 0.05, the moon's apparent size is larger than the sun at perigee and smaller than the sun at apogee. Thus, when the moon is in the closer portion of its orbit, total solar eclipses are possible, but annular solar eclipses are impossible. Whereas when the moon is in the further portion of its orbit, annular solar eclipses are possible, but total solar eclipses are impossible. Wherever the moon is in its orbit, partial solar eclipses are possible. In a particularly rare situation, the moon passes directly in front of the Earth while it is moving between the total eclipse and annular eclipse portions of its orbit. This double coincidental event is known as a hybrid eclipse, and only in these eclipses could part of Earth experience a total eclipse while another part experiences an annular eclipse. Also, even though the vast majority of solar eclipses move from west to east across Earth's surface, occasionally, a solar eclipse moves from east to west. Why? Because the Earth has an axial tilt, polar regions can experience a solar eclipse despite being on the other side of the axis. In fact, Antarctica experiences one of these rare east-to-west eclipses today. The Earth's moon is just large enough to allow the Earth to experience total solar eclipses. How about the solar system's other planets? Mercury and Venus have no moons and thus can't experience solar eclipses. Mars has 2 moons, but they're both far too small to allow Mars to have total solar eclipses, though they can produce severely underwhelming annular eclipses. Jupiter, though, has solar eclipses galore. All 4 Galilean moons are large enough in the Jovian sky to fully eclipse the Sun, though it's worth noting that only Io is in apparent size from Jupiter's surface larger than Earth's moon is from Earth's surface. Rather, the apparent size of the Sun from Jupiter is that much smaller than the apparent size of the Sun from Earth, so the bar is much lower as to the apparent size the moons need to meet to cause a total eclipse. The eclipses are also far more frequent given Jupiter's near lack of axial tilt and the moon's near lack of inclination. On Saturn and Neptune, even more moons pass the even lower bar for being able to occult the Sun, though per moon solar eclipses are less frequent from these planets' significant axial tilts. On Uranus, many moons can produce solar eclipses, but with Uranus's axial tilt and its moon's corresponding orbital tilt, they all only ever happen around Uranus's equinoxes. Since it takes Uranus 84 Earth years to orbit the Sun once, every 42 years Uranus experiences a deluge of solar eclipses, but then is starved for solar eclipses in the decades between the deluges. So, 5 planets of the solar system provide total solar eclipse opportunities. If you enjoy a solid ground to appreciate them from, though, you have one choice: here on Earth. Thanks to my Patreon supporters who make this video possible. If you also wish to help keep this channel running, please consider becoming a patron over at patreon.com/heirua. There is a link in the description. And as always, remember to love the night.